All right. So I want to talk about an interesting topic. Right? We talked about systems with 2 degrees of freedom, but you can look at this topic as a very interesting application for systems with 2 degrees of freedom. As I said at the beginning of the semester, we said we have, I think probably was the first class or second class. We said, well, I said, we have two types of vibrations, right? A type of vibrations that we're trying to get rid of, we're trying to suppress, we're trying to eliminate, and the type of vibration that we like, we want to keep, right? Examples from typical things that, as I said before, that if there is no vibration, we can't hear each other, right? Speaking, um, the way the sound wave propagates in air, and we can hear each other, the way the eardrums vibrates because of that air, because of the sound waves. Uh, these are kind of good vibrations, if for a lack of a better term, that the kind of vibration that we need. If they don't exist, right, we can't hear each other, we can't talk. Or if the kind of vibration that, or better to say, when we create music, right, that's the kind of vibration we want. When a string oscillates, it creates sound. We mix them together, we compose music. So that's the kind of vibration we want. As the more advanced example would be energy harvesting. That is the topic of your final project. We want to generate electricity from a source, a vibration source, or environmental source of vibration, or a source of motion. That's the kind of vibration that we want. We want to increase the vibration in that case, so we can generate more electricity, right? Now, there is kind of vibration that the main type of vibration, or the majority of vibration sources or situations that we're dealing with, are vibrations that we want to eliminate. Right? We said when you're riding a car and you're passing, let's say, a bump on the road, you don't want to feel that, uh, the motion or the oscillation in the car because of that bump. Right? So you want to somehow eliminate that vibration. If you have an electronic, let's say, device sitting on an oscillating, or vibrating surface or environment, right, you want to make sure that that electronic device is protected from that oscillation. You don't want your electronic device to oscillate up and down too much, because it might get damaged. So these are the situations that you want to eliminate the vibration. Now, we looked at one case when we talked about base excitation, and it was also one of your projects, that we use vibration isolation, right? When we have some kind of excitation in some base, and we're trying to protect, let's say in that case, an electronic device or a system sitting on that surface, we can use combinations of springs and dampers to isolate that system from whatever vibration is happening on the base. Like another example that we might have talked about, or might have shared some videos on a forum, is about earthquake. Right, when a building is, there is some kind of oscillation on the base, like on the ground. Right? They use combinations of dampers to isolate or dampen, or eliminate, better to say, that vibration, to protect the structure from that vibration. Now, that's one type, right? We talked about that basic citation, how to design, or how to come up with some kind of vibration isolator to um, reduce the effect of vibration on our system. Now, we're going to talk about the second type. Right? And the second type, the good thing is, because we talked about the systems with 2 degrees of freedom, now we can talk about this. And that would be vibration absorption. Right? Both of them goes under the category of vibration suppression. Right? We're suppressing the vibration. Either we're isolating that, or we are absorbing that. So let me put it under, um, let's say, vibration suppression. Let me see if I can. Vibration suppression. All right. So As a general description, I can give you some things to put there. Let's write it this way. We are trying to, or let's write this way, protecting a device from steady state yeah, that's good, harmonic disturbance at a constant, I think frequency would be a good word, frequency. That's at least what we cover in this course. We focus on a specific frequency. As long as we know what is the frequency of excitation in our system or an environment, we can come up with some kind of design for isolator or vibration absorber to reduce the oscillation, to protect the device. Now, we're not going to talk about vibration isolation because that's what we covered when we were talking about base excitation. So just mention that the first type would be vibration isolation. That's what we did when we were talking about base excitation, and again, you did a project on that, so you should be relatively comfortable with it. All right. We, if you remember, the whole idea was we had. Let me draw something here, just quickly. We had a mass. Let's say on a set of springs, the base was moving, let's say YT, and then we had the motion XT, right? And we had our springs there, let's say both of them together are K, so each is K over 2, and we had a damper there, the damping C. Right? Now, when we had the base motion, we could change the values for the stiffness and damping constants to get to make sure that the amount of displacement transferred from the base to the mass is minimal. The second one we're going to talk about today is, and that's new, is vibration absorption, which basically the whole idea is we design a vibration absorber. Well, let's put them in this way. Let's say vibration isolator and vibration absorber. Vibration isolator and vibration absorbers. All right. So what is the situation in this case? Now, in this case, we have, let's say, a spring mass system. Right? Vibration absorbers that we talk about in this, at least in the scope of this course, we're gonna stick to just the type that has springs. Now, there is a more advanced version that has both the spring and dampers, right? And there is a different way to design those absorbers. But we're just gonna stay with the type of vibration absorber that only has the springs. So our system is a mass spring system. Right? Some forces applied to it. Remember, base excitation of vibration isolators or vibration isolation. The case for that, the base was moving with some applied displacement, right? Some imposed displacement. Now we are talking about a mass. Let me draw it here. Now, our case now is this: we have a mass, right? Some spring, This is fixed. K over 2. K over 2. Now this one, we have a force applied to it. Let me put the force on the top of this. Then we have a harmonic force. And let's say it's Ft is F naught sine omega t. Right? This is a force vibration situation, right, for a spring's mass system. Now, what we want right now, the difference up to now is that this is fixed, the spring mass system, and there's a force applied to a mass, and there is no displacement to base. When does this happen? A very good case of this is when we have reciprocating pumps. I remember when we were talking about rotating unbalance, for instance. That was the case for that. When we have a rotating unbalance, because of that unbalanced situation, some force is applied to the system. When we have an electric motor is working, if there is an unbalanced situation in the motor, or other examples would be maybe compactors. When we use compactors in construction sites, we have the same situation. There's a force vibration, and we want to kind of absorb that oscillation. There are so many examples, and one of them would be the topic of what you saw as a topic of the second project, right? You will see there that even for small scale electronic systems that we can design vibration absorbers to actually reduce the vibration caused by some unbalancing or some kind of motion that is applying force to your system. So as a general case, we have some mass sitting on a spring being excited by some force. Now, this force can be caused by different, as I mentioned, different sources, from rotating unbalance to some unbalancing because of the shaft of, let's say, a turbine or a motor, or if you have some kind of compactor, or even you see this. It's a little harder to connect it to this concept, but the working principle behind is the same. You see this on these dumbbell shape absorber they put on electric cables. I don't know if you've seen it when you pass by these large electric towers. If you look up some of them on these cables, there are some kind of dumbbell-like absorbers that they put to reduce the vibration of these cables because of the wind blowing at them. And that's a safety precaution, because if you have a lot of vibrations in these cables, they start hitting each other and they might break, and all the problems that can happen because of that. So it's the same idea. That's actually also a vibration absorber, and the principle of that, the way they design it is pretty much similar to this. All right, so we have this case, right? Now, what we want to do, we want to get rid of this vibration, right? We want to reduce the motion of this mass because of the force applied to it somehow. Right? This force is applied, F naught sine omega t. So because of this force, this mass is going up and down, it's oscillating. What we want to do is that we want to absorb this motion. We want to get rid of this motion. Force is there. We want to make sure that this mass does not move that much because of this force. How do we do it? We add a second part to the system. We add a new spring right there and a new mass. Call it MA and KA. Mass for the absorber and the stiffness of the absorber. So this is the absorber we attach to the system. All right, we say, well, we already had that system. Let's take this spring and mass and attach it to the system. Now let's take it from there and see what happens. Let's look at the theory behind and look at the free body diagrams and how can we design. Now the goal would be to come up with a good combination of stiffness and mass for the absorber, right, K and MA, to be able to absorb the maximum amount, to minimize the motion of the main mass m as much as possible, or to reduce it as much as possible, to minimize it. Let's see how it can be done. Let's start with free body diagrams. I'm gonna derive the equations of motion for this system, and from there I'll tell you how can we design this. You'll see the process. Bear with me, the process, because the system with 2 degrees of freedom under force vibration can be a little long, right? But just make sure you follow the steps, right? I just want you to know and see how we go from what we have to what is the I would say final process to design the absorber for this system. So let's start with free body diagram for let's say for M, for this structure. I'm going to draw that right there. Let's put it there, and kinetic diagram there. This is M. This is M. Now I have to come up with some notations. Let's put the motion for this as XA, and I'm going to put the motion for the main structure as X. And it's a system with 2 degrees of freedom, so I have to make the assumption, right? Let's assume that X greater than XA. Now, if X is greater than XA, right, I'm going to draw this. Let me use a better tool. We said, well, when we make the assumption, we can assume that the one with smaller displacement is fixed for a moment. So M is going up, right? Because M is going up, Ka and both of these K over 2 stiffness or springs are trying to pull it down, right? Pull it back to its equilibrium position. So I'll put them right there. This one would be K over 2x, and the one in the middle would be Kx minus Xa. Hopefully you remember this. You're comfortable with this after dealing with systems with 2 degrees of freedom with drawing free body diagrams. Going up, this one is X is greater than Xa, so all these arrows would be downward. The magnitude for the spring between the mass and absorber mass, mass for the absorber, is the if you always keep it positive, right? The magnitude we keep it positive. So K times X minus Xa. And let's not forget that we also have a force applied to the system. That's also up there. That's F naught sine omega t. On the other side, well, it's accelerating upward, so that's all we have, M X double dot. So if I write the equation of motion, summation of forces in y direction is equal to M X double dot. I took that as X direction, so let's just be consistent and say this is X. I didn't even have to put anything there. I can just a summation of forces. There is only one direction, so you guys know what I'm talking about. All right, let's take positive. Upward is positive. As we said, we always take the direction of the motion as positive. So that would be minus K over 2x, minus K over 2x, minus Ka X minus Xa. And plus F naught sine omega t is equal to M X double dot. If I move things around, I'll get M X double dot. Let's take these to the other side, plus K plus Kax minus Kaxa is equal to F naught sine omega t. That would be my first equation. This was for M. Now let's take a look at the second degree of freedom, which is XA. Right? Let's draw the free body diagram for MA. Let me go to the next page. For a free body diagram for MA. Going back, let me just draw it here first. So this would be MA and MA. Free body diagram and kinetic diagram. This is MA. This is MA. Let's see what we have there. We only have one thing, which is coming from this spring, and it's in opposite direction. Right? We had KAX minus XA on M, so we just flip it and put it on MA. Right? That would be KAX minus XA, and it's also going upward. So there is the component XA X double dot XA double dot. So summation of forces is equal to MA XA double dot. Right? It's upward. KA X minus XA is equal to MA XA double dot. If I move things around, MA XA double dot plus KAX, move it to the other side, minus KA, plus, this would be plus KAXA minus KAX is equal to 0. Hopefully I didn't make any mistake. This is the second equation. System with 2 degrees of freedom. I have the equations of motion. Naturally, the second step would be to write the equations in matrix form. Right? So in matrix form, let's this is the mass matrix, and let's go with X double dot, XA double dot. These are our 2 degrees of freedom. Stiffness matrix, I'm going to make it a little bigger. X and XA, and we have the force component. Mass matrix, well, first line is coming from the first equation. We have M right there, so that is M. No XA double dot in the first equation. For X and XA, XA coefficient is K plus KA, and the other one is minus KA. K plus KA minus KA. And in this case, we have force on the right side. So F naught sine omega T. F naught sine omega T. Right. Right. Let me move this. For the second line, second equation. So there is no component for X double dot. Component for XA double dot is MA. Then we have minus KA, KA, and no force on that side, so 0. Pay attention, as I said, always mass and stiffness matrices should be symmetric, right? It's symmetric here. If they were not symmetric, I would have gone and checked my equations of motion. Something something would have gone wrong there if I had some matrices that they were not symmetric. All right, so that's it. Now we have to solve this. We are looking for, remember what I said. I said we are looking for a steady state response. All right, I'm going to go back. It says protecting a device from steady state harmonic disturbance at a constant frequency. So I don't care about the transient response, what is happening at the beginning of the motion when things are still not stable. All right. Now my goal here to design this, in order to design this vibration absorber, is to find the good values or correct values for MA and KA. Remember, this is the absorber I'm attaching, right? Some mass, the amount that I should know, and some spring KA that I should know the stiffness for that. How do I do that? Well, to figure that out, we have to solve these equations of motion for a harmonic input, and then take it from there, and we'll just figure out how can we actually find the response, right? So here's what I'm going to do. I'm going to say, well, we want to find a steady state, right? I'm going to take these as a general form of a solution. So to find the steady state solution, let's take these. Let's say xt is some x constant, right? It's a harmonic input. So since the input is harmonic, the output should also be in the harmonic form. And we're talking about just a steady state. So we forget about the first part, whatever is going on because of some initial condition. And that would be xa sine omega t. So just take these as general forms. I'm going to plug these back. Right? If I plug this back, I can, let's take derivative. Two derivative to have that would be sine omega cosine minus omega squared x sine omega t, and x a double dot is minus omega squared x a sine omega t. I'm going to plug these in my equation, matrix form. Let's write it this way. That'll be m 0 0 ma x double dot, let's write it as minus omega squared x minus omega squared xa. I'm going to take sine omega t out. Plus, or matrix, stiffness matrix would be minus ka, and ka. For x, I'll put x and xa and take sine omega t out is equal to, well, on the other side, I can write it as f naught 0 sine omega t. Right? It's a vector multiplied by constant. So every component gets multiplied by the vector. I just take that out. If you do the multiplication, we can just take this sine omega t's into the vectors, and each component would be multiplied by that. All right, so let's rewrite this, right, in a better form. I'm going to write it in this form. I'm going to write it k plus ka minus omega squared m. That will be minus ka minus ka. I'm just putting those matrices together. I'm just doing the summation pretty much and factoring sine omega t out. So if I factor sine omega t out, I can just sum of these two matrices. To sum a matrix, to sum two matrices, sum of two matrices, just sum of their elements. Right. I did this multiplication. I'm just skipping some steps. I did this multiplication and then this multiplication. Right. So that would be minus m omega squared x. The next one would be 0, 0 minus ma omega squared xa. And then summing up these two 2 by 2 matrices. What I get from here, just going to write it here. Make sure that m, this would be minus m omega squared, right? This would be 0, this would be 0, this would be minus ma omega squared, and this is going to be x and xa. Right? If you do that multiplication, then I sum up the two matrices. Ka, and this one becomes Ka minus omega squared ma. And this is x and xa. Sine omega t is equal to f naught 0 sine omega t. So both sides, right? I have sine omega t. I can just say, well, let's forget about that sine omega t. It's pretty much the same, right? I'm not interested in knowing where that is zero, because if that's zero, then it's always everything is zero. So I will keep in mind what I'm trying to do. I'm trying to find x and xa, right? This is what I'm trying to find. Trying to find this. That's what I'm trying to find. I want to know what is the amplitude of vibration under some given force excitation. Now, this is a matrix operation. Right? Think about it like this. We have, if we ignore sine omega t's, right? Here is what we have. In general, we have, if I call this A, matrix A, we have A times X is equal to something, right? Vector F. How do I find X now? I can multiply both sides by A inverse. If you multiply that, you'll get A inverse F. Depends on how much linear matrix multiplication and linear algebra you remember. This is coming from that. Right? If you multiply both sides by A inverse. Now, inverse of a matrix multiplied by a matrix itself gives you a diagonal matrix, just one as diagonal elements, and everything else is pretty much zero. So that gives you pretty much just X, vector X. And on the right side, you get A inverse times F. Again, depending on how much you remember linear algebra, you may or might not find it confusing, but hopefully you remember this much. Now, if we do that, let's find A inverse first. A inverse, remember, this is a 2 by 2 matrix. So although these are like parameters there, I don't have numbers, but I can still find the inverse. If this is A, we said AD minus BC, remember the components, 1 over AD minus BC multiplied by switching the components on the diagonal or diagonal elements and multiplying the off diagonal elements by a minus 1. So I'll do the same thing right here. It's divided by 1 over determinant. And the determinant of that would be multiplication of the elements on diagonal elements. So that would be Ka minus omega squared m. That would be K plus Ka minus omega squared m multiplied by Ka minus omega squared ma, Ka minus omega squared ma, I have to make it a little longer, minus Ka squared, minus Ka squared. Right, let's just put this in the middle. There you go. Now the matrix itself, right, we said right there, we're going to flip diagonal elements, switch them, and multiply the off diagonal elements by minus 1. So that will be Ka minus omega squared ma. Right, so this becomes Ka minus omega squared ma. This is Ka. This is Ka. And the other element would be what we had at the top, K plus Ka minus omega squared m. K plus Ka minus omega squared m. This is A inverse. Now, to find X, I have to multiply A inverse by F, or force vector. In this case, well, I'm talking about F naught and 0. I just divided both sides by sine omega t, or got rid of sine omega t. That's not what I was interested in. So this gives you let me put it this way, x and xa becomes 1 over what be right there, k plus ka minus omega squared m times ka minus omega squared ma minus ka squared. If you multiply this vector by f, that will give you ka minus omega squared ma, or let me write it this way, ma omega squared, ma omega squared f naught, and the second part becomes ka f naught if we do the multiplication. Remember, we're multiplying this by f naught and 0. So it's a 2 by 2 multiplied by a 2 by 1 vector. All right, so here's what I got. Now x, right? So x, what is x? X is the displacement sorry, of the main structure after attaching the absorber. Let's write it. So x is ka minus ma omega squared f naught divided by k plus ka minus omega squared m multiplied by ka minus omega squared ma minus ka squared, and we get xa2, displacement of the absorber itself. That will be ka over f naught divided by, same thing, k plus ka minus omega squared m, ka minus omega squared ma minus ka squared. These are what we were looking for. Right? Now, for a given harmonic input force, F naught sine omega t, the first one would be the displacement. All right, this is the amplitude of the displacement of the structure. I'm talking about m. This one is the amplitude of the absorber, ma. Right? We got the displacement. So for any given input force, remember what this system was? For any given input force, F naught sine omega t, when we attach the absorber, these are going to be the displacement for the structure and displacement for the absorber. Now remember what the goal was. We attached the absorber to minimize the motion of the structure. The structure is going up and down. We attach the second spring mass here as the absorber. And this one is supposed to absorb some of the vibration. So this is going up. When we attach the second one, because of the second one's motion, some of the energy from the main structure is transferred to this extra spring mass we add. So it's released or it's absorbed, it goes into this part. As a result, the motion of the main structure reduces. I can think about it as an extreme case if we have, they both are in totally out of phase situation, meaning that when this goes up, this goes down. So when this wants to go up, this is going down and pulling it down. When the main structure wants to go down, this one is coming up and pushing it up. So it reduces the amount it oscillates because of this counter effect it has on the main structure. Right. Theoretically or mathematically, these are the displacements we get. Now, To minimize the displacement or the amplitude of displacement of the structure, what do? Well, very simple. We make this x, this amplitude of displacement, we make it equal to 0. We say I'm looking for some MA and KA, mass of the absorber and stiffness of the spring for the absorber. I want to find the values that make the displacement of this structure 0. So make it equal to 0, see what we get for Ka and Ma, or what relationship you get for that. So the goal is to minimize x, right? Displacement of the main structure. What are we going to do? So let's put x equal to 0. Right? We have x. Let's put x equal to 0. When we put x equal to 0, well, what is the numerator? That should be 0. So Ka minus Ma omega squared times F naught should be 0. Right? So Ka minus Ma omega squared times F naught should be 0. Well, F naught is just a constant, so it doesn't matter. It's just a number. That is not 0. If it's 0, there is no motion in the system, right? There is no external force. The steady state, there is nothing happening there. So we make Ka minus Ma omega squared is 0. As a result, we get omega squared as Ka over Ma. This is the golden relationship that you are looking for. So if you know let's say this. If you know the frequency of excitation of your external force, right? Let's say your system is under force excitation with a harmonic force excitation with a frequency of 10 radian per second. The value of the stiffness for the absorber and the mass for the absorber, to make sure that your structure doesn't move, right, because of this force, this counter effect is strong enough to make sure that the structure actually doesn't move. It is under force vibration, but whatever force is trying to do with your main structure is transferred or is absorbed by the added absorber, spring mass system you added. To make sure that that happens, the frequency, there should be this relationship between the excitation frequency and absorber's mass and absorber's stiffness. So as long as your Ka over Ma, right, the stiffness of the absorber, mass of the absorber, this fraction, is equal to omega squared, right, your main structure doesn't move, which is perfect. That's what you were looking for, right? You were trying to get rid of the vibration in your main structure. All right. So this is the relationship you need. Right? This should be the relationship between the excitation frequency and absorber's mass and stiffness. Now, if you look at it, what is this? This is actually natural frequency of absorber. Right? If you look at absorber as just one system, right? What is absorber? Absorber is, well, by itself, before attaching it to a system. Absorber is nothing but the spring mass system, right? Ma, Ka. So this omega is basically omega of your natural frequency or natural frequency of your absorber. Absorber by itself, before attaching, is just a single degree of freedom system. It's a spring mass. So omega A is equal to K square root of Ka over Ma. So that's pretty much is also the natural frequency of the absorber. So the frequency of excitation to your system should be equal to the natural frequency of your absorber. In a perfect case, to make sure that your system doesn't move. So you have a structure under some force vibration going up and down. Whatever the frequency of excitation for that force is, right? Your absorber that you design should have the same natural frequency. The natural frequency of that should be equal to that excitation frequency. Doing that, you will get the minimum displacement. Perfectly, if you're exactly that same frequency, zero displacement in your structure. Now, let's find out what would be the, if that is the frequency, what would be the displacement of your absorber? If this is achieved, let's put it this way, then XAT, well, we know XAT is XA sine omega t, becomes, what becomes? It becomes, if you put the value there, or XA, we got it as this fraction, KAFA. So let me write it here. XAT becomes KA F naught over that long fraction, but in this case we put omega as omega n, as omega A, sorry. So this becomes K plus Ka minus m omega A squared, right, times what else we had there? Ka minus ma omega A squared minus, what was the last term? Ka squared. Ka squared. Now, look at this Ka there. Right, what do you get for Ka? Well, from here and here, from both of these equations, either, let's go with this. We have omega squared is equal to Ka over Ma, and as a result, Ka becomes Ma omega A squared. Right? We say this is omega A. So if you replace that as Ma omega A squared, this becomes 0. This is 0. Let me write the rest, sine omega t. So this whole fraction, you can simplify that as Fa over Ka sine omega t. Or let me write it separately so I can actually, Xat becomes a minus Fa over Ka sine omega t. This becomes, that's not what I was looking for. This becomes the displacement of your absorber. This is the displacement of absorber. Now, why is it important? When you are designing, there are design constraints, right? The problem is this is the displacement, and this part specifically becomes the amplitude or magnitude of displacement of absorber. Why is it important? Because when we design it, let's say you come up with an absorber that is natural frequency the same as the frequency of excitation, so you minimize the motion, or again in a perfect case you make the motion of the main structure zero. Now the problem that comes up, right, is that you have design constraints. Let's say you are putting this, you have some table in a lab environment, and you want to minimize the vibration of this some specific equipment on the lab table by adding a spring mass at the bottom or below the table. You just add a spring and a mass there to absorb the vibration in the table to make sure that the table is not moving. Right? You're doing some sensitive measurements. Well, the problem is in so many cases you have limited space. Right? You have, let's say, 50 centimeters, a meter under the table. You need to find out the displacement of the absorber, or the amplitude of displacement of the absorber, to make sure that this amplitude is not more than the space you have. Right? You put the spring and mass there, and this spring and mass starts oscillating. The absorber oscillates and absorbs the energy from the main system. The higher the energy in the main system, right, the longer or the bigger this amplitude. This mass spring has to go up and down, right? Maybe more with higher amplitude. But you have design constraints, right? You can't have, you have to make sure that you also meet that design constraint. Your absorber is not moving a lot to hit the ground, or let's say hit the table. Well, hit the ground mainly, right? So that's why you need to find the displacement of absorber. Now, we'll go over an example. We'll see how the design process works. Now, this is for the perfect case. This is for the case that the harmonic input, the excitation input, is very well known, and we know that the frequency of excitation for the harmonic input stays exactly the same. Let's say if it oscillates, if the force has 10 radian per second as its excitation frequency, it always is 10 radian per second. It does not deviate from that number. It's exact number. Now, in reality, the excitation force frequency obviously changes a little bit, right? It might go from 10 radian per second to 9 to 11. There might be some oscillation there, right? Driving frequency might shift a little bit, to one side to another. Right? How do we deal with that? Right? So that's where the concept of bandwidth of operation comes into play. What is the bandwidth? What is the frequency range that this absorber you designed is effective? All right, so you designed it for 10 radian per second. The question would be, is it going to work well when the frequency is 11 radian per second, or 12 radian per second, or 8 or 9 radian per second? How does this perform? That would be the next question you have to answer. Right? And we'll figure that out. So let's say the excitation must be well known and doesn't, let's say, deviate from its constant value of frequency. Right? In that case, this vibration absorber works perfectly fine. Now, the driving force, one couple of problems can happen. Now, let me put it this way. Now, one problem that can happen is the driving frequency. The driving frequency, whatever is the frequency of the excitation, can shift a little bit. And then, since we are going to remember, we are going from a system, single degree of freedom system, spring mass system oscillating, to a 2 degree of freedom system. Right? We have two masses now. It's a 2 degree of freedom system. So system used to have one frequency, natural frequency. Now it has two natural frequencies, right? Because it becomes a 2 degree of freedom when we attach the spring and mass. Now, what problem that might happen or might occur is that if the frequency of the excitation gets close to one of the frequencies, that would, in that case, it's not a good situation, because we are adding the spring mass damper, we are making it a system with 2 degrees of freedom. What if the frequency moves a little bit, excitation frequency, and suddenly gets close to the one of the natural frequencies? Then we're going to have a resonance, right, in our 2 degree of freedom system. So one problem is driving if driving frequency, in parentheses, frequency of excitation shifts to one of the natural frequencies of our 2 DOF system, then we're going to have resonance. Not good, right? Suddenly we're going to have huge displacement. Something else to have to keep in mind, you have to keep in mind, is that this is the case that there is zero damping. We designed this absorber for zero damping. Now, if there is damping, the magnitude wouldn't be zero. Right? This assumption was based on no damping. We said, well, if there is no damping, this is the x, make the x equal to 0. This is the frequency. So if your absorber, if your excitation frequency is equal to the natural frequency of your absorber, zero displacement. But that's the case for no damping. If there is damping, just keep that in mind. You don't get zero magnitude displacement for your primary structure, as they call it, primary mass, or main structure. All right, so we're going to answer this question now. Here is the question. How much deviation in driving force the absorber can tolerate? That would be the question we have to answer. We designed it for a specific frequency. Now the question would be, well, how much I can deviate from or get away from this design frequency and still have an effective absorber that can absorb the vibration in my structure? That's something we're going to talk about in the next class. We'll talk about this in the next class, and then I'll go over an example or two and I'll show you how the whole process works and how can you actually use this to design the absorber for a specific application. And at the end of the class, we're going to have our quiz. Remember, the quiz covers systems with multi-degree of freedom. Right? We're going to have that at the end of the class on Thursday. All right.